Hello everyone. I'm Chen Qiao. Thank you very much for taking the time to join our session today. Today, Yunfei and I will discuss mobile rendering optimization, integrating traditional methods and new approaches. We hope that through this session, we can provide you with valuable information and inspiration. Now, let's start today's session. First, let us briefly introduce ourselves. I'm Chen Qiao from Tencent MoFun Studios, Yunfei from Tencent XR Vision Lab. In our collaborative project, DR Toolkit, we explored the application of differentiable rendering technology. Today, I will introduce our work, and then Yunfei will take over to the share of the practical implement. Today's session consists of the following parts from background and traditional methods to differentiable rendering and its applications. Part 1, why we need rendering optimizations. First, let's examine the development of GPU performance in mobile devices and the release date of iconic game on the market. As performance has improved, the type of games has evolved from early light and casual ones to more heavy and performance-intensive ones. Although hardware performance continues to improve, the computation demands of the games has also increasing. As mobile device performance approaches that of consoles and PCs, more games are demanding multi-platform crossplay. Achieving a console-like visual appearance on mobile can significantly enhance competitiveness in cross-platform game development or porting console games to mobile. A device in computation power and energy consumptions across the platforms lead to a varying game asset specifications. Quickly generating assets based on the artistic design can significantly reduce the development cost and improving efficiency. Additionally, optimizing game performance on low-end devices and minimize the requirements for entry-level devices can make games more competitive in emerging markets. The strategy not only enhances the performance but also ensures better competitivity and user experience across a broader range of devices. Our optimization goals are to reduce hardware requirements, decrease computational consumptions, avoid significant visual differences. This optimization will directly expand the player bases, enhance player experiments, and ensure fair competition. Additionally, we increase the potential for multi-platform crossplay. Rendering optimization is very important, so what are the common methods we use? Let's take a look at the difference between mobile devices and PC. In a PC, the CPU and the GPU are mounted on the motherboard and powered by a 400-watt supply with a dedicated cooling system. In contrast, mobile devices, due to energy efficiency consideration, integrate the CPU, GPU, and other modules in a SoC system on chip and operate with a power bucket for only 2 to 3 watts. PC GPU generally use immediate mode rendering IMR design, which data directly write from buffer, resulting in a high memory bandwidth requirements. High bandwidth implies high energy consumptions and a significant heat generation. To avoid this issue, mobile device GPU use a tiled-based deferred rendering (TBDR) design. TBDR divide the screen into tiles and process only one at a time. This approach requires loading and processing data only for the current tile, which enhances the utility of the on-chip cache, reduce bandwidth pressures, and improve energy efficiency. Effectively leverage this TBDR design and reduce the GPU load are the two important measures for rendering optimization in mobile devices. Let's examine how the game engine renders a counter C. The entire process can be viewed as a series of selection and reduction of the game scene content, retaining only the visible elements. Then these are passed to the driver in a GPU-friendly way for the rendering. We need to eliminate the invisible objects and the triangles to reduce unnecessary GPU computations when ensuring minimal changes in the visual output. This process is called culling. At the object level, culling can involve freeze-time culling, which removes objects outside the field of view or too small, and occlusion culling, which removes objects occluded by others. Occlusion culling is significant for free-of-view shooting or action games. It typically involves software rationalizations, GPU occlusion queries, and PVS, potentially visible sight. Different types of games can choose or mix these approaches. After identifying the visual object, we need to sort them in a GPU-friendly way to maximize the hardware efficiency. For instance, different types of drawable objects should be grouped based on their materials and textures and so on. Rendering opaque objects from near to far can reduce the calculations for occluded pixels, and grouping objects with the same rendering state can minimize the state changes. Additionally, use a render graph to organize the rendering process is crucial. A rendering graph represents stages of the rendering pipeline in a graphical structure, allowing developers to define rendering dependency and data flow clearly. It enables a more controllable and efficient arrangement of rendering tasks, optimizing memory and resources management, reduce context switching, and improve bandwidth efficiency. Our game contains a large number of resources that can be merged or reused. The merging technique allows us to combine multiple objects with the same material type into a larger object and render it in a single draw code. Instancing allows us to render multiple indicate objects with a single draw code, setting the geometry data once and efficiently render it multiple instances. For example, foliage in the scene and the building constructed with prefabs can be utilized this mention. We also consider offload commutations that are easily parallelizable from the CPU to GPU to improve the overall efficiency. For example, the vertex scanning calculation from scanning meshes can be performed on the GPU. Additionally, animations can be converted to data textures to avoid bottom update calculations. Furthermore, instancing can be utilized to render swarms of monsters as shown in the bottom right figure, thereby expand the gameplay possibility on the mobile devices. Similarly, to alleviate the GPU's burden, we need to optimize art asset to enhance rendering performance. For mesh assets, it's important to avoid overly small triangles and use as few triangles and vertices as possible to achieve the same visual effect. During the render phase, minimize the byte size per vertex is crucial for bandwidth optimization. Additionally, addition should be paid to create LOD level of detail assets. For textures, it's advisable to consolidate the texture channels to reduce unusage channel and to set appropriate texturing compressions and simulating modes. We also need to focus on optimization for the shader code. Pay attention to data preparation, efficiency use built-in function, and minimize ALU operation counts and their corresponding cycles, providing relatively simple LOD implements for the rendering algorithms, and the manifold of if condition branches and the situations that may trigger later Z issues. Additionally, it's important to manage the number of shader variants. Here, some metrics we should ensure as much as possible based on the action actual condition. In practice, we need to use GPU analyzer tools like ARM Performance Studio for tracking and adjustment. Efficiently leverage mobile GPU's TBDR design and reduce the GPU load are the two critical methods for the rendering optimization in mobile devices. So it would be highly beneficial if we could produce asset for low-end devices to reduce GPU load. Next part, differentiable rendering is a novel technology that can provide such assistance. In the core of differentiable rendering is to make the rendering process differentiable, which allows for the computation of derivatives which respect to the certain parameters such as camera positions, lights, material, shape, and textures, and so on. During the rendering process, this enables optimization methods such as gradient descent to adjust the model or fit the parameters. The computational process of differentiable rendering has two paths, the forward path and the backward path. The forward path is similar to the traditional rendering, where it inputs the parameters and converted into a 2D image with accelerated data. The 2D image is compared to the target image, and a specific arrow function evaluates the rendering result. The backward path is a step unique to differentiable rendering. It involves computation the output gradient with respect to the input parameters from the forward path. The gradient is used to optimize the input parameters in the loop, approaching the target image result. However, the concrete implementation of this technology faces some challenges. One of the main challenges is computing derivatives. Currently, we have three methods. The most straightforward approach is to manually calculate the derivatives and write them in a code, but the approach is not flexible in the game development. Another approach is to utilize the automatic differentiation features of deep learning frameworks, but these frameworks are designed for network training, not other than graphic problems. The third approach is to use automatic differentiable languages specified for graphic problems, with DRGIT and SLAM-D being leaders in this field. Another major challenge is handling the discontinuities in rendering. In academic communities address this issue by redesigning the rendering-related algorithms. Similar to traditional rendering, there are Monte Carlo-based methods and rasterization-based methods. The two main implementations of the rasterization-based differentiable rendering are soft-res and NVDefrost. Soft-res introduced soft-resization and aggregation functions to solve the discontinuity in the XY screen space and the Z-deep direction. NVDefrost achieved a differentiable rendering system based on deferred shading through basic operations of a custom graphic pipeline. Based on this foundation, a series of projects and applications has been derived. In gaming industry, there are already several cases where differentiable rendering has been used. For example, last year, Mr. Hajime Uchimura introduced BRDF measurement fitting using differentiable rendering. The owner of the King team shared at GDC how they utilize the differentiable rendering for resource production. SLAM-D promotes a shared ecosystem between the machine learning and the graphic hardware rendering system, encouraging the exchange of the components and the ideas from the different fields. This bound to have a significant impact on the industry. How can we use differentiable rendering to optimize the resources? This process is similar to the training process of a neural network. Resources transform and optimizations based on differentiable rendering also include similar steps such as data preparation, model model definition, selection of loose functions and optimization algorithms, training our fitting loops, and model evaluation and deployment. These steps can be briefly explained as follows. 1. Export resources from the engine to an external differentiable renderer. 2. Perform the fitting loop with the external renderer. 3. Return the fitted result to the engine project. In this particular application scenario, it is necessary to consider applying this process to a third-person shooter games. Third-person shooter games is a common genre that typically involves elements such as shooting, combat, and tactical movement and character movement. Taking Synced as an example, the cameras in the TPS games are bolder and varied, and the map is large. As shown in the bottom right figure, peoples have many nano-monster enemies. To support this game design, the programming and the artist team have done much work. Similarly, this design also poses a challenge to our transformation task. Existing differentiable rendering handles game results ineditably. We modified them to better fit the usage pattern of game resources. Additionally, we conduct fitting for the materials, meshes, and global parameters. We need to extend the differentiable render from a single mesh version to a multiple meshes version. The basic steps of the differentiable render are indicated in the left right. To support the rendering of multiple meshes components, we add a sorting, merging, and blending section shown in the light purple. To handle shadow-related content, we have incorporated the light resource shading calculations, use a ray tracing method similar to NVDiff-RECMC. This part is displayed in yellow. We add a material translation section shown in the light blue to process many custom materials. We sort the components in the rendering based on whether they need optimization and their material type. First, we render opaque objects that do not need optimization. Next, we render opaque objects that need optimization. Then we sort and render all transparent items from far to near. After rendering is completed, we merge the rendering result. Furthermore, transport object needs to be rendered use a peeling method to ensure accurate blend result. In construction text, cameras capture the scene using a roughly uniform half spherical distribution. This method of viewpoint distribution is not suitable for TPS games. We need to determine the camera position and directions based on where the player are likely to be and their viewing directions. We categorize the sources of cameras in 3 types: viewpoints from generated on menu placed information like points, peaks, and splines. Viewpoint generated based on navigation meshes. Viewpoint generated based on mesh information. Based on these previous generated cameras, we fitted the current track asset. As you can see, compared to the origin PBR material, the fitted material retains the detail. The roughness, AO, and other information from the PBR material are reasonably integrated into the current fitted texture. But by using only basic Lambert diffuse lighting, we can achieve a similar appearance. Here, we are fitting the result of the reflection part. As we can see, this part of effect is missing because screen space reflections do not participate in the fitting. Of course, this kind of effect is also turned on low-end devices. However, static IBL can be preceded in the fitting and achieve an approximate appearance. As shown in the figure, the fitted texture on the well hub is brightened by the IBL lighting. In actual application, many textures are tiled. These textures are not only tiled, but also be reused by different objects. We use debug mode to display the usage of this tiled material on the buildings. In such cases, it's difficult to determine the camera position and directions for processing, so we handle those textures separately. For vertical walls and horizontal floors, we perform the fitting based on their usage direction under a neural ambient light. In this appearance of the wall, this is the appearance of the wall after the fitting. For the window and glass areas, the internal mapping method is used to achieve the corresponding reflection effects. This area does not precipitate in the fitting process. This is the texture, the original albedo textures and the fitted textures. Let's take a look at the detail of material sources. As shown in the figure above, materials from game project are very complex and with custom node connections and custom HLSL code nodes. Therefore, to achieve the effect same with the engine and the external differentiable rendering, it is necessary to translate the engine material to the external differentiable rendering and achieve the same computational effect. For custom node connections, we remove branches related to platforms or quality levels irrelevant to the fitting, and fix parameters that can be treated as constants, and disable dynamic effect related to the gameplay. For custom HLSL code, it is needed to be vectorized and converted to an automatic differentiable shading code. As shown in the left figure, in translation HLSL, we not only translate the code from the editor, but also attempt to directly translate the shader from shader toy to achieve the same rendering effect. As shown in the right figure, the materials and with the node connections, we can fit on the static appearance by sprite, gameplay, and dynamic effect, and then overlay the dynamic effect afterward. I will hand this session to Yunfei. He will tell you more details.
Hello everyone, I'm Yunfei. I will cover applications and experimental results. First, let's examine how we apply the techniques mentioned above to the master's appearance in the game. The master's material is one of the most complex materials in the game. Although the master is composed of multiple parts, we use vertex color blend with a texture array to complete the rendering in a single draw call. Additionally, to achieve the gameplay required effects, gameplay effects are overlaid into the upper layer. These are the comparison appearance after our fitting process. The left side shows the fitted appearance without overlaying gameplay. The middle shows the fitted appearance with overlaying gameplay. The right side shows the original appearance. Only the static image of the master is shown, with the gameplay effect overlaid. The blue gameplay effect logically resembles the indicators on Ultraman's chest. This gameplay effect is not involved in the fitting process, but is overlaid during runtime. This is a comparison of the normal involved in the shading calculation. To reduce computational cost, we only use vertex normal for the fitted material. Here, the comparison between the fitted base color and the original base color are shown. This is a comparison of one of the textures in the UV space. The fitting process has added some geometric shape and lighting information onto the base color. Similarly, we conducted experiments on the entire scene. The above is the standard rendering mode, while the below is the minimalist rendering mode, in which only vertex normals are used for ambient diffuse lighting calculations. After fitting, the metallic or metal-like parts will contribute part of the reflection results to the fitted texture. Non-metallic parts will overlay some AO and normal shading effects on the fitted texture. Here we can see more results, because without dynamic real-time reflection, the intensity of the reflection will be reduced. Here, the stone parts are overlaid with some AO and normal shading appearance. The minimalist rendering mode only uses vertex normal for diffusion lighting. Without pixel normals, the calculation of tangent space is omitted. From a performance perspective, in our fitting process, we use a method similar to IBL normalization to overlay highlights on the diffuse texture, avoiding highlight calculations. When lighting is a computational bottleneck, this optimization has pronounced effect. This optimization is user-friendly and does not require significant engine changes for low setting effects and LOD effects in a forward rendering pipeline. In a deferred rendering pipeline, if high precision is needed, additional data for base color may be required, making modifications complex. In deferred rendering, replacing just one or two objects to coexist in high and low setting resources has a limited effect. Using fitting resource is best switched as a whole. When switching globally, there are significant advantages in performance and video memory. On low setting devices, PCs, and mobile devices, the optimization effect is notably pronounced. The game runs at 720p resolution and 30 FPS without other changes. On mobile screens, the slightly clearer visual appearance of fitted texture is more acceptable than lowering PBR texture resolution and simplifying PBR shading effects. For synced, we can make a mobile version from the PC version, and they all look similar. For global parameters, a differentiable rendering-based method can also be used to fit parameters between rendering systems. However, this parameter fitting method is more independent and may not require rasterization-related operations. Taking atmospheric scattering as an example, the effect of atmospheric scattering is generally considered to be the overlay of sky color with the atmospheric perspective effect. However, calculating atmospheric perspective is inefficient and difficult to achieve on mobile platforms. The mainstream approach are as follows. Number 1, non-physically accurate algorithm. However, the parameter of this algorithm is difficult to adjust. Number 2, pre-calculation. Number 3, physically accurate ray tracing solution. This method has high computational load for mobile use. Our approach simplifies by using the effect obtained by a physically accurate algorithm as baseline, and then fit the parameters for a simplified, non-physically accurate algorithm that achieves the same visual appearance. How are these parameters obtained? We aim for a physically accurate approach and fit the parameters required to the simplified algorithm. The iterative fitting process is shown on the left. Our fitting method eventually achieves a very good balance between performance and realism. Although differences still exist, the effect meets the requirements. This is the atmospheric scattering fitting effect at dawn. To facilitate comparison, we capture the parts where atmospheric scattering is most visible for a unified comparison. The top row shows the atmospheric scattering effect on a PC. The middle row shows the effect on the fitted effect. The bottom row shows the effect without scattering. When fixed at the intermediate time period, it can be observed that the fitted result is close to the atmospheric scattering effect on a PC. From a practical project perspective, the current UE engine and DCC pipelines provide relatively mature LOD solutions for their specific use cases. However, these solutions do not optimize for the final appearance of objects. We attempted to enhance the original visual effect using a differentiable rendering approach. We tested resources within the project. The middleware used was unsuitable for LOD 4-level resource processing due to its algorithm characteristics. Manually created resource and UE-generated resource were already very good before adjustment. For manual resources, the fitted materials improve the details. For HLOD resources, since we do not want them to have normal map when in use, we improve the effect by correcting the vertex normal and the texture of the existing resource through differentiable rendering, enhancing the appearance without normal maps. For non-traditional mesh processing, we attempt a modified continuous remeshing approach for mesh simplification. Continuous remeshing is a method that uses differentiable rendering for remeshing. This method processes optimization from cost to phi, continuously adaptive remeshing the surface. Compared to other methods, this technique can generate finer meshes more quickly with fewer defects, less parameter adjustment, and the ability to reconstruct more complex objects. We enhance area control by using vertex color from the original model and extended mesh partitioning control. For example, as shown in the above figure, more triangles can be distributed in areas requiring more detail, such as facial features and ears. Currently available AI 3D model generators are rapidly improving in quality, allowing us to obtain detailed 3D models, such as the horse shown in the slides from the surface. The backend algorithm has advanced to create hard surface geometry using 3D diffusion, followed by generating detailed texture through 2D diffusion models. The generated mesh still employ algorithms similar to matching cubes, which results in more details and more faces. However, from a performance standpoint, we prefer fewer faces. If we apply traditional mesh simplification algorithm to these AI-generated models, such as quadric edge collapse deformation with texture, the result tends to be unsatisfactory due to artifacts like duplicate faces that hinder the algorithm's ability to simplify the mesh uniformly. To make it work, first we need to clean up the mesh by removing duplicate faces and ensure the mesh is manifold. Only then can we effectively apply the quadric edge collapse deformation to achieve a functional mesh, albeit in a low poly style. Next, for the texture, we use differentiating rendering to rasterize the original mesh. Then we need to solve the closest barycentric between the simplified mesh and the original mesh. This allows us to create the base color texture and the normal map for the simplified mesh. After that, we can combine the texture and the geometry together. The comparison illustrates the outcomes. The left image displays the original generated mesh with 125,000 faces. The middle image shows the simplified mesh without a normal map, reduced to 2,000 faces. The right image features the simplified mesh with a normal map, maintaining the 2,000 faces while retaining details comparable to the original mesh on areas like the feet. The final part is summary and outlook. We have modified the differentiable renderer to fit the usage habits of game assets better. For the numerous complex materials and texture resources in the project, we created a translation framework for material resources. We perform the layer separation and the layer fitting on the material to achieve complex blending effects. For global effects, we apply the differentiable rendering to fit atmospheric scattering effects. For thin mesh resources, we attempt to generate and refine LOD resources and test it on IGC assets. These are some practices we implemented in the project using differentiable rendering. Future prospects. Moving forward, we will focus more on the development of following aspects. Number one, better engine integration, such as integrating the strata material system. Number two, the development of more comprehensive differentiable graphics framework. Number three, better applications in general AI. These are the reference materials we mentioned in the topic. As the session draws close, I want to express our heartfelt gratitude to our team and partners. We sincerely appreciate their efforts and cooperation in the project. We particularly thank the developers of prior technologies whose contributions have laid an essential foundation for our work. Thank you.
Question?
Yes.
Is this current research that Tencent is researching, or is it something that's available for us to play around with and try out?
Maybe we have a open source version this year, maybe next year early. Yes,
So in the sort of next 12 months, it'll be something that we can get our hands on and play with ourselves?
Yes, it's a collaborative project in Tencent games. So we can open source some demos or codes for other developers. But there is only the differentiable part of our project. In real project, maybe we call our project DR toolkit. So it's a toolkit. Maybe in a real project, it should be a tool for plugin for PCG pipeline or for maybe a Unreal game package pipeline. We make the low-end asset, and they will make the packages for these devices. We only introduce the differentiable part, but the asset package or PCG pipeline is in other team. So we only show this. Yeah. Yes. Currently, we are moving our code for Slang-D version, so it's more easily used and can be integrated into other games or engines easily. Yeah.
Does this differentiability allow us to improve inter-frame blending and adjust camera pose to VR headsets after the frame has been rendered?
Sorry, can you repeat?
So the frame has rendered. Can you take the derivative with respect to camera pose and adjust the camera pose slightly after the frame has been rendered? For example, for high motion VR headsets.
这是还能是。
他是说那个渲染的角度如果变化太大的话，会不会有影响
？The angles is a problem, but for our game we symboled the importance of we make an importance for each angles, and the different angle may have different white values. In the final loss function, they will balance the value of the camera view. So we make a catalog for the directions, because in a game, the player is on the ground and seeing forward. So this view is very important, but maybe on the top view is less important. So we reduce the top view's whiten.
I mean, for very small
Yes.
Headset phones?
It's okay and it's acceptable. It's acceptable in our games because we use IBR normalized method to normalize our textures.
Did you say you were seeing sorry, anybody else? I don't want to hog the floor. You're getting 30 frames per second, is that what you were aiming for on mobile platform with differential, yeah?
Yes,
so
yes.
Not so much for mobile, like for VR?
For VR, for mobiles and for VR is also acceptable because we change the PBR material to a much cheaper version. There is another benefit for this because maybe we have a full PBR shader, but we have a much light shader. But the light shader material or the parameter for the light shader, our artists didn't want to adjust limit for this asset. So this technology can transfer the parameters for the high-end devices to the low-end devices. Maybe we take the atmosphere scattering for the example, because in an open world and game and with TOD, with time of day in it, the artist will adjustment too many parameters, so they don't want to make a parameter group for the high devices, for the middle devices, and for the low devices. Yeah. It's very heavy.
Yeah, the outer sampling.
Yeah.
So when you're calculating your loss function, you basically you have to preemptively set up on a spline or wherever you're seeing like typical camera positions.
Yes, we use the camera positions as a pool. When the loop, we select some cameras from the pool.
Yeah.
Not in the batch size is not so big. The batch size is acceptable on NVIDIA video card.
Okay, and this has to be done per scene as well, correct? Like when you calculate your loss function.
Yes.
Yeah. Is there a specific loss function per environment?
No. The loss function is another complicated problem because when we want to make some material or texture optimization task, we may put more white for the pixel loss, but maybe for the mesh related, maybe the age is very important also. So for this different task, we set different weightings.
Would you be able to go back to the references page just so I can get a picture of it?
Yes.
Yeah.
This one. This one. Next page. The third page.
Thank you.
Lots of shader toys.
Yes, we use the shader toy as a benchmark.
That's good fun.
Yeah, yes, because we didn't know whether we process the shader correctly.
Yeah,
so we use the shader toy as a benchmark. We put the reference of the shader toy on this. Our programmer, this framework programmer asks each writer in the shader toy. Yeah. So we can put it here. This framework is developed by Xianglan, Dreamman, the second one.
Okay, thank you.
Thank you.